What's going on, guys? Hope you're having a great day, and welcome to today's video. Today we're going to go through part 2 of the Iris Dataset, where we're going to finish off the tutorial. Circled in red, we have what we're going to cover in today's video, where we learn how to split, train, and test the data, and then we're going to learn to build numerous ML models and determine which one is best fit for our data. You're also going to go back over a little bit more of Jupyter and getting more familiar with Scikit Learn, but we covered a lot of that in the first video. If you didn't see part 1, I'll link it down in the description below. You should definitely check it out so you can follow along with this video. So let's get into today's video. We hop back in right where we left off last video at data visualization. So we'll do a quick debrief of where we got up to last video. We started with importing the required dependencies, loading the Iris dataset, summarizing our dataset, peeking into our data, and then doing some stats and looking into our data even deeper. So now we're at data visualization. So the goal of data visualization is to see how our fields and our features correlate together, so we can see what type of model we're going to end up wanting to do, whether we do a linear model, a non-linear model, and stuff like that. So we'll hop right into it. So we did EDA up above, which is exploratory data analysis. We're going to want to do a visual EDA here, because we're going to plot. So we're going to do our graphs. We're going to do from pandas the scatter matrix. So pd.plotting.scatter matrix. And what this does is this allows us to, exactly what I said before, see how each feature within our data set correlates with the other feature and see if we can see any patterns. So we're taking our data frame, correlation on our Y, so our features, because we want to predict which, on our targets, on our labels, which is the Y, because we want to see when our features correlate together, how it affects our target, our classified iris. And we'll set the fig size to 10 by 10. Our S is 150. And then we'll just set our marker to a nice, easy one as D. So we run this. It might not run depending if we need to import scatter matrix. Oh, no, it does. Perfect. So we see this nice, clean, crisp graph with our features on the left and our features on the horizontal axis. So really we can see that where these bar graph kind of looking graphs are is when it correlates to itself. So sepal length and sepal length, stuff like that. But what we really want to look at is how sepal length and all the other features, or feature to feature, how they correlate with other features, because that tells us how they're related. So we can see right away there are some linear trends, like petal length to sepal width seems to be petal length, to petal width, which is what you expect, seems to have some linear relations, as well as sepal length to petal length. So the lengths looks like they're kind of correlated linearly. You can see as sepal length increases, petal length looks to increase as well. But then there's ones like this, sepal width to petal length, which really doesn't have correlation. It's all over the place. A bunch of them, you can see that are all over the place. So this tells us that our data is kind of a good mix, that we could probably use various different linear and non-linear models, which is why I actually chose this data set, so I can show you how to do some linear models and some non-linear models. So that pretty much is it for our data visualization. We can see that we can implement both types of models. So let's move on to our evaluator algorithms. So I've gone ahead and populated some text to cover what we're going to go over in this section, in the evaluate your algorithm section. So in this section, we're going to cover splitting our data into our training and our test set. We're going to set up validation using 10-fold cross-validation method, which I'll explain down below. We're going to build 6 separate models for predicting the iris type based off the features, and then we're going to determine the best model for the data. So I've also gone up into the import dependencies and added a lot more Scikit Learn Scikit dependencies that we're going to need. So you're going to want to go up here and copy these down. These are all the models we're going to use, and then scoring and report metrics for determining which model is the best. Yep, so let's head on down. So split our data, B, open a new one. Let's set up our test set size. So I recommend that you do between either 80 and 70 for your training set. So the rest should be your test set. So I'm going to do 80 for my training. So I'll do test set 0.2. That means my training is 0.8. What you want to do is set a seed value. I'm just going to set it to 7. Setting a seed for this next line allows it so that if you keep rerunning your model over and over again, the test set will remain the same values and your training will remain the same values. So that way when you keep going back and forth, you can keep the results the same between models, like you're not splitting your different test and training sets. So it's a good best practice to do. So we're going to use train test split from Scikit to split our data. So xtrain, xtest, ytrain, ytest. This is going to split it into our different training and training label, testing data, and testing labels. Train test split is the function from Scikit that we've imported up above. Takes in our features, our labels, and now this is where we do our test size. So equals just test set size. And the random state is where we put the seed so that all of our models are going to have the same training and test data, and it's not going to jumble it all up. So we go Control Enter to run that. Perfect. So now we can move down to actually doing our cross-validation. So what I mentioned above, we're going to be doing 10-fold cross-validation. This is a technique to determine the effectiveness of your training. So what it does is it actually takes the training data set and splits it into 10 parts, or folds as they call them, and then it uses one for validation and the rest for training. And it iterates through and does this for all different combinations. So it'll take the first 9 portions, train with that, validate with the other one, then take this the next 9, validate with the first one, and it'll rotate through all the different combinations and really validate our test set, or our training set rather. And what this does is it allows us to keep our test set pure, unbiased. We won't keep going and validating on our test set. We keep it pure until we're ready to actually test and see whether our model is good. And this allows us to tune hyperparameters like the learning rate or batch size in our training and not have to do that in our testing set. So that might be a lot thrown at you, but it's just good to know that 10-fold cross-validation just allows us to keep our test set aside and not use it until we know that our model is good enough to be used on the test set. So now we're ready to build our models. So like I said before, we don't know exactly which type of model is going to be best at solving our data set. From the data visualization, it appeared that some variables are linearly separable. So we're going to go ahead and just use 3 linearly separable and 3 nonlinear separable models. So the algorithms we're going to use are logistic regression, which is a linear model, linear discriminant analysis, which is also a linear model, k-nearest neighbors, which is nonlinear, classification and regression trees, nonlinear, Gaussian naive Bayes, nonlinear, and support vector machines, which are linear. And I'll have future videos where we go in depth about these algorithms and how or what they're actually doing. But for this, it's just an intro video. We're just going to show you how to create different models using these and then see if they're any good. So pop up a cell, create a list of models. So So models equals empty. Now we're going to go ahead and start adding in our models. So models.append, and this one will be our top one, logistic regression, label LR, and then logistic regression, which is, if we go up here to the top in our dependencies, we see that we have imported from Scikit Learn a linear model, logistic regression. So now we can just call logistic regression and get the functionality of creating a model. So solver equals lib linear. These are just Scikit terms to distinguish what type of model we're wanting. And it is multi-class because we have different types of irises. And we'll set that to auto so it does it automatically. And we'll run that to see if it works. Okay, yep, no errors thrown. So we can continue on, and we'll just do this for each and every one. So I'll come back when I've done it for each and every one. So I've gone ahead and appended every model into our models list. So you can see that we have all 6 of these. So now we can go ahead and actually cross-validate on them. So we'll have a results list, empty, and a names list is empty. And now we're going to loop through our models and train. So we'll set up a for loop for name and models. In models, we are going to want to do the cross-fold validation. So kfold equals kfold from Scikit Learn. Our number of splits is number of folds. We want to do 10. 10-fold cross-validation is a good best practice and usually works the best. And then we're going to do our random state to our seed that we named above. This way, every model is using the same data and it's not jumbling it. So now we're going to do our cross-validation results equals our cross-val score from Scikit, which takes our model, our X training data, and our Y training, which is the labels. And then we set cross-val equal to the kfold we just created. And our accuracy metric is, or our scoring metric, is going to be accuracy. So this will give us a percentage. So then we have that. Well, let's create our results and add each one to our results. Perfect. And now we're going to go ahead and just start printing stuff. Well, actually, first we'll append the names into our names list. And now we can set up our printing message. So our message, we'll do our %s. %s, there we go. %f, %f. So this is just setting up our print statement to look nice. If you're not familiar with percentage symbols and how to format print strings, then I might create a video for you on that. Let me know down below from this video what you guys want more explaining on, and we'll go over it. So we're going to do the mean across each, because as I said before, it's going to split into 9 training and 1 validation. The training data into 9 training and 1 validation, and keep iterating through all different combinations. So we're going to want to take the mean from that, and then we're also going to want to we'll print the standard deviation. And from these values, we should be able to see, oh, I didn't print it. Let's go ahead and print it. Oh, let's go ahead and actually print the message. And oh, we want to do model and models. Okay, perfect. So now we can see the standard average accuracy on the validation set. So we're getting 96.6% accurate for our logistic regression, our linear discriminant 97.5, our KNN's 98.3, which is super high. Our cart is 96. Our naive Bayes is 97.5, and our SVM is 99.1. Wow. And we can see that our standard deviation is really, really low on this one, and it's pretty much the same on all the rest. So that's evaluating our algorithms on the training data. So this will predict how well we're going to do on the test data and whether we're ready to go to the test data. These are all super high and show that linear models and nonlinear models are both good on our data set, on the Iris data set, for predicting the Iris type. So for making predictions and doing our testing, I'm just going to move forward with the top two. So I'll move forward with k-nearest neighbor and support vector machines. Because it's the same thing for each way to test it, we're just going to show and choose which actual one is the top of the best of the best. So yeah. So we'll start making predictions. We'll start with our K and N. So we'll set up our model again. So K and N equals our K neighbors classifier. And we're going to train on the whole training set. We're not going to do the cross-validation anymore. We'll just use that to see which model would be good moving forward. And now we're going to use the whole training data to train. So set up that. We go K and N. We use Scikit Learn's .fit. This is how you train your data for the full set. And you do X train and just Y train. It's that easy, and you run it. And you can see it's auto, the leaf size. This is all just defaulted. It defaults to the nearest neighbor is 5, which is usually best practice, relatively strong and good and nearest neighbor size. So we're going to go with that. So that's the training. That's all. It's simple as that. You just set up your model, and then you do .fit and give it pass it in your training data. And now we can do predict. So we'll go predictions equals K and N on our model, predict, and you give it your X data of the test set. You don't want to give it the Y because it should be guessing that. And now we go score K and N equals our accuracy score from Scikit, where now we give it Y test and predictions, and it will give us the score of how well it did. Oh, I gotta do print score. Okay, cool. So that shows us that when we train the model and then predict using the test set, we have an accuracy of 90%. So out of every 10, we're getting 9 right, and 1 is mislabeled. So that's pretty good. So we're going to do now go in a little deeper and actually use a couple tools to see which ones we got wrong and where our model went wrong. So this is called, we're going to print the confusion matrix and the classification report. So confusion matrix will give you a matrix showing like false positives, false negatives, positive positives, like true positives and stuff like that. So you can see which one it went wrong on, and same with classification, it's going to tell us the accuracy and the weighted averages. So confusion matrix equals this method from Scikit. These are all from Scikit. They're all in the dependencies that we put up above. And then we're just going to give it Y test and predictions same as our scores. And we're going to go print. We'll let you label it, which is what's look nice. Confusion matrix. Skip a line. Oh, nope, it's called confmat. And then our classification report is the exact same thing. It gets the y-test and predictions. And we will print it the exact same way as well. Skip line. So here's our confusion matrix. It shows that we had, so the first column is we had 7 of our first iris type in our test set. So let's go up and see what our first type is. Our first type is Setosa. Second type is versicolor and virginica. So for Setosa, in our test set there were 7 of them, and it got them all right because there's none that it guessed wrong. For the second iris, there was 11 of them, but it guessed 2 of them as the third type, and there was 9 of our third iris, and it guessed 1 of them to be the second one. So that's 3 got wrong. 2 here and 1 here. So this gives us, this is the precision, that's the confusion matrix, the classification report. It gives us all these values and shows our average, like it shows us that we got 100% on the first, on label 1. And then it shows all your averages and weighs them so you can see. So we're going to do this exact same thing with, so we're going to do all of this again with our SVM. So I'll just grab that. I'll quickly put Markdown as SVM. So now we'll change this over to SVM. So SVM equals SVC, and it takes in as gamma to be auto. And change this to SVM so we can now train it with our full set. Perfect. These are the default parameters showing you what SVC takes in. So now we're going to do our svc.predict. I'll just call predictions 2. svm.predict. And we give it our x test, same as before. And now we'll do our score SVM equals our accuracy score. And we'll give the y test and predictions. And now we will print our score. Oh, I definitely named something wrong. This is predictions 2. What is going on? Oh, a good old typo. So we can see that actually our SVM is 93% accurate on the test set. So it's actually looks like it's better than our KNN. So we're going to do the exact same confusion matrix on the SVM, print it in here, and I'll just label everything as 2. Conf 2. Takes in predictions 2, class rep 2, class rep 2. Okay, so we can see which makes sense. Our test set is the exact same as before, but that we got 100% on the first two and only one wrong on the third. So it averages out to 93% accurate. So in conclusion, do a little markdown. Conclusion, make it a header 2, that since the accuracy on our SVM model was greater than that of our KNN model, and I'll put in brackets what percentage they were. (93.33%) and 90. That our SVM, or I guess we can say, since our SVM model is 93% was greater than that of our, it can be deemed that the SVM model is best for our data set. It best represents our data set, as it is almost perfect, highly accurate. And that's that for this video, guys. So from start to finish, we've gone over a lot, I know. We imported our required dependencies, load our data set, summarize our Iris data set. We can see our 4 features, and then we can do some analysis, some stats, some data visualization, and then we can, from our data visualization, evaluate different types of algorithms using cross-fold validation to see which we want to move forward with and train fully. So we chose KNN and SVM as they were the highest rated. And then from there, our final step is to make predictions. So we use our test set, train our models on our training, and then predict using our test set, and then use an accuracy score from Scikit, and then that will give us the accuracy on our test set. And then we can do some reports and matrices to visualize it better and see where it actually went wrong and see what our test set was layout like. And then in conclusion, we can deem that one model is better representative of our data set and trains it best. So yeah, I hope you learned a lot in this video, guys, and I'm looking forward to creating more content for you. Let me know down in the comments below what kind of content you want to see, and smash that like button. Thanks, guys.